This is lesson 3 of motion. Please start by pausing the video and doing the quick quiz. Okay, pause this video and check and correct your answers. So far this topic we have learnt a little bit about speed, and you can calculate speed given a distance and a time, and you can also use distance time graphs to tell you about speed. In this lesson, we're going to look at the speed of particles and the speed of waves. We've learned about particles and waves in previous topics, and we're going to tie that in with what we've learned about speed. Okay, the first thing we're going to do is we're going to recap states of matter. Now, we talk about states of matter. There are three states that we talk about: solids, liquids, and gases. And what we do is we imagine that atoms are just circles. So here are my states of matter: solid, liquid, and gas. Those circles represent atoms. Now, actually, we know that atoms have a nucleus in the very centre that's very, very tiny. And in that nucleus, there are protons and neutrons. And around the outside, there are shells, and electrons orbit or go round the nucleus in shells. We know that about the atom, but to make things easier when we're drawing diagrams, we're going to just draw them as circles like you can see. So in a solid, the particles are in a regular array. That means that they're really neatly organised in lines. They're in fixed positions. They can't flow. They can't move anywhere they want to. They are fixed. If some energy is transferred to them, then they are able to vibrate around a spot. So they don't flow anywhere, but they can vibrate as a unit. Now, we can see that all the particles are touching, and they're all really, really close together. There aren't really any gaps. There's no space for more particles. And we call that dense. Solids are very dense. All the particles are very, very close together, and there's no room for extra particles to be put in. A liquid then in the middle, all the particles are touching. However, they are completely disorganised. They are randomly arranged, and they also can flow. Now they move, individual particles, they move in random directions with random speeds. Random just means you couldn't predict. So if you took one particle, you wouldn't be able to predict where it was going to go or what speed it was going to travel at. And we also know that liquids, they take the shape of the container that they're in. So if you pour a liquid from a long, thin container into a short, wider container, the liquid will take the shape of that container. Finally, gases. Gases are able to move very, very quickly. They have a lot of kinetic energy. This means that their speed is quite high. You can see that they're not very close together, so we say they have a low density. They move in a random motion and at random speeds, and they will fill the container that they are in. So if they're squashed into a smaller container, they'll squash in. If they're put in a bigger container, they will spread out. They'll fill the container that they are in. Okay, so don't write any of this down. I just want you to have a look at it. Pause the video and just read through the descriptions underneath each state of matter. Now, I'd like you to see if you can write down the description of each state of matter from memory. Okay, check and correct your answers. If you only got a couple for each of them, try and add in some more that you didn't get. So you can pause the video to do that. Okay, here I have used balloons to model a solid. So you can see that these balloons are neatly organised, they're all touching, and so they're a good model for a solid. Now, what is it that's holding these balloons together? just have a think for a few seconds. What is it that's holding them together? So maybe it's blue tack, maybe it's sellotape, maybe it's glue. But whatever it is, we can't see it. We just can see that they are all stuck together. Now this is sort of like what happens in a solid, except we don't have glue holding the particles together. We don't have sellotape or blue tack. We have what's called intermolecular bonds. Here, intermolecular bonds are invisible but really, really strong, and they hold the particles together. When we draw a diagram, you can see on the right, we represent intermolecular bonds with just short little straight lines in between particles. Intermolecular bonds. Now here we have balloons representing a solid, a liquid and a gas. And this starts to show that when a solid becomes a liquid, the bonds have either broken or become much weaker. These particles are further apart, they can flow over each other, and so the bonds, the intermolecular bonds that were really strong in a solid, are actually quite weak in a liquid and even weaker in a gas. So let's have a look at the changes of state. So if we take water as our example, we've got solid water over here, which is called ice. And if I add energy to that, then the energy will be used to break down those intermolecular bonds. And we call that melting. And we get water or liquid. If I add more energy to the liquid, the bonds, the weak bonds, are able to break and the substance becomes a gas or water vapour in this case. We call that evaporation. If I have a gas and I remove some of the energy, then bonds start to form again. And in that case, it becomes a liquid, and we call that condensation. If I take a liquid and remove even more energy, more bonds start to form. And so it becomes solid, and we call that freezing. Pause the video and have a go at these questions. Okay, on the next couple of slides are the answers. So have a look at this, pause it, make sure you check and correct. And check and correct this one as well. Okay, here we have a beaker of water or a glass of water, and these circles represent water particles. And what we know is that this is in a liquid state. I know that because the particles are all touching, but they're disorganised. Now, what we know about liquids is that they do have some weak intermolecular bonds. Intermolecular means the bonds between particles or between molecules. So I'm representing the bonds with these lines here. We know that they have weak intermolecular bonds. We also know that they can flow over each other and move around. Now, all of these particles, they're all moving at different speeds, and some are going really slowly and some are going really fast. Now, what happens is if a particle is moving or has enough kinetic energy, it will be able to break the bond that it has. So let's say these two are bonded together. This particle here in red, I've used red to show that it's got a lot of kinetic energy and therefore is moving quite fast. If it has enough kinetic energy, it can actually break the bond between it and another particle, and it can move away from the liquid. Now we call this evaporation. This is when a particle has enough energy to break the bond with another particle and become a gas. Now, like I said, these particles have ranges of speed. Some are going slow, some are going fast. This one down here, also in red, is going really fast, but it's not at the surface. And so what this one would do was it might break its bond with this one because it has lots of energy, but it might then collide with this one here and make a bond. And the same with this one down here that's also red down here. This one has lots and lots of energy, and so it might break its bond. Let's say it was bonded with this one, it might break the bond there, but then it'll collide, it'll be moving really fast and collide maybe with this one, and it'll form a bond with this one. So evaporation happens when particles have enough energy to become separate from the rest of the liquid and they become a gas. Now what this does is it means that the rest of the particles, the total kinetic energy of the particles left is less, because one of these particles with lots of kinetic energy has left and it's become a gas up here. So the total kinetic energy of the particles that are left is less, and that means that the temperature of that body of liquid, that glass of water, is lower. So when things evaporate, the rest of the liquid cools down. Now, if you think about when you sweat, you're doing exercise, the reason that we sweat is so that the liquid, the water, can evaporate from our skin, meaning that the rest of our body cools down. If you've ever been swimming and you've left your hair to dry and you haven't dried it using a hairdryer, you'll notice that you get cold. And this is because the water is evaporating from your head and cooling your body down. This situation is different. Here we've got a container of water again, and the circles represent the water particles. However, this time, the vast majority of particles have lots and lots of kinetic energy. This means that they're all moving around very, very quickly. And this is when a liquid is boiling. Now, the temperature at which this liquid boils will depend on what liquid it is. So I can tell you that water boils at 100 degrees Celsius, but different liquids boil at different temperatures. If we were to transfer any more energy to this body of liquid at this point when it's boiling, then very quickly the particles would evaporate. Very quickly the particles would have enough energy to break their bonds and turn into a gas. Pause the video and have a read of the description of evaporation and the description of boiling. Pause the video and have a go at these questions. And pause it to check and correct your answers. Okay, we're now going to have a look at waves and how they travel and their speeds. So here we have a diagram of a wave, and this is something that you need to know. So we're going to very quickly recap it. We're going to do a little test and then we'll have a look at the speed of waves. So the peak of a wave is the highest point of a wave. The trough is the lowest point of the wave. The amplitude is the distance from the middle to the top of a wave. The wavelength is the distance between two equal points on a wave. Normally, we measure peak to peak. So it's really important that you know these properties and a couple more. So the frequency of a wave is the number of waves passing a point per second. So if 5 waves passed per second, that wave would have a frequency of 5 hertz. Wave speed is the speed of the wave, and time period is the time for one wave to pass a point. Okay, pause the video and try to write the description for the property from memory. Okay, check and correct your answers. Okay, we're going to have a look at the speed of a wave. And we're going to do that. We're going to start by looking at the equation that we learnt at the start of this topic for speed. And that is that speed is equal to distance divided by time. And we used S for speed, D for distance, and T for time. Now, when we talk about wave speed, we use the letter V. So wave speed is going to be the same. It's distance divided by time, but the unit for distance, or the measure of distance in this case, is one wavelength, because that's a distance, it's a length. So wave speed is wavelength. That is a distance, it's measured in meters or centimeters. Divided by time. Now, the time period in the topic of waves is the time for one wave. So I could say that the wave speed is equal to the wavelength divided by time period. That's the same as saying wave speed is equal to the distance divided by the time. It's the same equation. And so we say V equals lambda, which we use for wavelength, divided by capital T, which we use for time period. But there's another relationship that we can use here. And that relationship is that the time period, so the time for one wave, is equal to 1 over the frequency. The frequency is the number of waves per second, and time period is the time for one wave. And they are related like this. This is a 1. So what I can do is, let's put this in symbols. T is 1 over F, frequency. Time period is 1 over frequency, 1 divided by frequency. What I can do is I can put this T here into here. So that would give me an equation that looked like this. Wave speed is equal to wavelength divided by 1 over frequency. 1 over frequency. Now actually I can rewrite that so here we have this equation, and actually I can rewrite that. When you divide by 1 over something, that's actually the same as timesing it. So I'll show you what I mean. Wave speed is equal to wave length times by frequency. And if we were to write that in symbols, V is equal to lambda times F. And that's the wave equation that you learnt when you studied waves. And I've just shown you where it comes from and why it's the same when you work out wave speed as when you work out speed using distance and time. Let's just quickly go through the units. So the unit for wave speed is meters per second because it's a speed. The unit for wavelength is meters. And the unit for frequency is hertz. Okay, have a go at these questions from memory. Check and correct your answers. Okay, let's have a look at some problems. And when we do problems, you'll need to know that you might need to use the speed equals distance over time equation, or you might need to use the wave equation. And it will depend on what you've been given as to which equation you need to use. So it's really important that you copy how I set this out and you do exactly the same when you do yours. So a wave has a frequency of 2 hertz. So I can write down F for frequency is 2 hertz and a wavelength of 5 meters. So I can write down lambda for wavelength is equal to 5 meters. What is the speed of the wave? So we want to know V, the wave speed. So the equation is V equals F times lambda. Wave speed equals frequency times wavelength. Wave speed is equal to 2 times 5. So in this case, the wave speed is 10 and the unit's meters every second. So this wave is travelling 10 meters every second. Let's have a look at this one. If a wave has a speed of 5 meters per second and a wavelength of 0.2 meters, what's the frequency? So this time we've been told that the speed is 5 meters every second. So V is 5 meters every second. The wavelength is 0.2 meters. What's the frequency? So we still use the same equation. Wave speed is equal to frequency times wavelength. And we put in the numbers that we know. So wave speed in this case is 5. We don't know the frequency, but we do know the wavelength. And so what we'll do to solve this is we will divide both sides by 0.2. And so into your calculator, you'll do 5 divided by 0.2. And that gives me a frequency of 25 hertz. Let's have a look at this one. So here we've been given a speed of 4 meters per second. That means that the wave is travelling 4 meters every second. So V is 4 meters every second. And we've been given a frequency of 1.5 hertz. 1.5 hertz. And we want to find the wavelength. So the equation is wave speed is equal to frequency times wavelength. In this case, the wave speed is 4 meters per second. The frequency is 1.5 and we don't know the wavelength yet. And so we will divide both sides by 1.5. And so into my calculator, I do 4 divided by 1.5. And when I round that to 1 decimal place, I get a wavelength of 2.7 meters. Okay. A sound wave is produced by a speaker and is heard by someone standing 500 meters away. It takes 2 seconds for the sound to reach them. What's the speed of the sound wave? So in this case, we've been given a distance between the speaker and a person. So I can write down d for distance is 500 metres. It takes 2 seconds for the sound to reach them, so the time is 2 seconds. And we want to find the speed. So speed is equal to distance divided by time. Speed is equal to 500 divided by 2. And so the speed is 250 metres per second. That means that this wave is travelling 250 metres in every second. So now you're going to have a go at the worksheet and you'll have a mixture of wave equation and speed equation questions to do. Each time you must write down your workings out, your answer, and then the unit.